Okay. So today what we will do is we'll cover about basics of casting. Hopefully I'm clearly audible, right?
Yes, sir.
Yeah, good. And the students, they are still in the other class, or they are coming back. The number of students is around, I think, 15 right now. That's fine. I think we'll start now. So basically, this class, what we'll do is we'll cover about casting basics. Then we'll talk about patterns and molds, and then there is some analysis. We'll talk about melting and pouring analysis, and then solidification. Because melting inherently is a process where you pour molten material, and then we let it solidify. And then there will be some defects and remedies which we'll talk about. So that's what is in the outline for this entire casting thing. So basically, if you remember, we showed you some casting in the first slide. Right? In the first class, we showed you some of the things where things were being cast. One was the wheel, which was cast, and the engine. If you remember, the cylinder was cast. Right, the engine cylinder was cast. So the biggest casting in automobile is still the cylinder block is still cast, and of course the wheels were cast. So basically, casting is a metal object obtained by pouring molten metal into mold and allowing it to solidify. So that's what basic casting is all about. Okay, so before you go into main details, we will show you one animation about explaining the basics of casting. Let me just give me a minute. I'll start it. Is it audible?
And a code print. This demonstration provides useful understanding the following steps. Take a hollow boxes, rectangular in shape, called cope, and drag. Place the wooden pattern as shown in the animation. Fill with sand in layers and ram for equal distribution of sand and compactness.
This is a pattern, and there is cope and drag. There are two boxes, and the pattern is split into two. So this is the other half of the pattern, because you have to take the pattern out. That's why you split it into two parts so that you can take it out.
Invert the boxes and remove the pattern.
So you can take the pattern out now. So you will have two symmetric hollow things. You put it back and then pour the metal to get the full shape. So you are splitting it because you got to take it out and create a cavity of the solid part which you want. So you got it out. So you got a hollow cavity on both sides. And if you want a,
and it is supported by core print.
So core basically is this portion, you want it hollow. So you have a solid thing. So you can create the hollow shape by using a core.
Pour the metal and fluid is filled as shown in the animation.
So basically, wherever the core is, you will get
geometry.
Hollow shapes. Now you have a product with a hollow shape of the core inside. You can break the core and get a product. So this core can be broken. Inside is a hollow shape. So this core can be broken and you can get this hollow part.
A sand casting pattern is similar in shape to the cast product. A sand mold cavity is a negative replica of the pattern and is produced by packing sand around the pattern. Core. A core consists of two portions, the body of the core, one or more extensions called prints. The prints are necessary to support the core in the mold. They also conduct the heat and gases produced by a sand core to the mold. Core print. The print is an extension of the core body, usually along its axis. The print design depends on the direction of the core axis and the number of openings. Each opening corresponds to a separate print for core support.
So print is just going to support it, right?
The print must balance the body so that the core stays in place during mold assembly. The print must not shift during mold filling. The print should minimize the deflection of the core. Unsymmetrical holes should have foolproof prints to prevent incorrect assembly. The print should maximize the heat from the core to the mold. The print should allow the internal gases generated in the core to escape to the mold. The prints of adjacent cores may be combined into one.
Okay, so I'll just stop here. So now you have a fair bit of idea what basically.
Sir, there is a question.
Any questions here?
Question in the comment box. Sir, how was the core removed finally?
A core you can break it. So since you have access to the core, right? Because the print will be there from top, so you can go ahead and use a chisel, hammer, something to break it. So core can be broken. You can take some sort of a chisel or something and break the core out of it. Core always have access because it's a hollow thing, right? The problem would be if it's a closed hollow thing, then it may be difficult. In that case, what people do is then you will have to do something else. But typically what happens is you need to have an access to the core. Otherwise, if it's hollow inside, then there may be difficulty to break the core. But you typically have access to the cores. Okay, so cores can be broken. But if it's say in some cases you have a totally closed kind of a thing, then you will have to make casting such that your closed hollow, then you'll have to figure something out to. There are other methods in that case. I'll show other ways to do it. Then you can have the mold itself like that, where you can have the hollow portion can be so the hollow portion will not remain in the mold. So you'll have to figure something out with that one. There are other ways. I show you some other methods to do that. But in most cases, you have access to the cavity to break it. Okay. And then I'll tell you there are other methods wherein you can create shapes which have enclosed cavity. That's a challenging one. Okay. That's also there are ways to do that also. So did I answer the question or?
There are two more comments. One regarding the core itself and second one is sizzler.
What is it? Yes. So if there is no requirement for hollow, then you don't require the core. The core is required only for having hollow things, and core is nothing. It's made of solid sand only. You use a binder and with the sand and slightly more, and you basically sinter it a little bit so that it's stronger. It's actually sand only. Okay, but you require core only and only if you want hollow. What is sizzler? What do you mean by it has axis, then it can be removed? No. So sizzler. Let me go ahead. I did it say about sizzler?
I think you talked about chisel or hammer.
Chisel, not sizzler. Chisel, cheni, hathoda.
Okay,
chisel,
sir.
right? It's not sizzler. Chisel.
Yeah, it's okay, sir.
Okay, it's cheni. If you don't understand in English, okay. You just need to knock the thing out if you have access. If you don't have access and you want totally closed hollow thing, then you need to have some different methodology for it. Okay, I'll talk about other methods for that. There are other casting methods for that. Okay. Right?
Yes, sir. What type of sand is required because molten metal is going to be poured? There is another.
No, sand is a refractory material. So I'll talk about that also. Sand is a refractory material. Sand can take very high temperatures. Okay. So you don't need to worry about sand. Sand is actually silica, and silica is a refractory material. It can take more than 3000 degrees centigrade. So, but typically you want sand where you can have enough strength. So you need sand, you need binder, and you need good quality sand to do casting. I'll talk about what kind of sand you need. So let me just go ahead. This was just a brief overview of what kind of did I start the recording? Oh yeah, yes, good. Yeah. So basically, casting is a very old process. So the first reference of casting, if you see in history, is in 3200 BC. So a copper frog has been found in Mesopotamia. Mesopotamia is nothing but modern day Iraq. And then cast iron plowshares have been found. Plowshares, you know, right? What is plowshare?
So can you make presentation full screen?
Oh, sorry, I'm sorry. So plowshares, you know what a plowshare is?
Sir, I don't know.
So plowshare is hull. Those things which is known for tilling the land. So Chinese made a cast iron plowshare way back in 233 BC, and Indians could make in time of Aristotle, Greeks imported all the swords from India because Indians could actually make wrought iron. They knew how to forge and cast. Okay, so that's how the iron was cast, and then they used to forge it, so they can make very good, very strong swords out of India. So they were able to cast and deform. And then cast crucible steel in India was done in 500 AD. And if you see, US, the first cast steel by crucible was done in 1818. So you are able to do it 1300 years before. In fact, we have some of the steels, like I don't know if you know about this Mehrauli pillar, right? This pillar is made of steel, which has not corroded in 1500 years. Probably it's Gupta period, 1500 years, and there's no corrosion in the iron which they have created. Still a wonder for a lot of these metallurgists. And then first iron casting was at Lynn. Lynn is right next to Boston. And 1919 AD, initially all these were done by electric furnace was not there, right? These were all like coal-fired furnaces before. So 1919, the first arc furnace came into US, and then in the 70s they did something called semi-solid metal working process, which basically is nothing but a combination of casting and forming. And then in 1996, metal mastic composites were cast. So basically, casting was done for metals with ceramic particles in it. Okay. So the advantages of so So the advantages of casting is that you can create near net shapes, and then you can do low scrap casting, and also you have relatively quick process. Casting can be done very fast. It can be used to create integrate shapes, and in fact you can also create large hollow shapes, and there's no limit to size. So basically casting is as big as you want. You can create castings, and you get reasonably good surface finish. So if you want to understand the dimensions of the casting, at least sand casting you can do as large as you like, and you can do small 1 millimeter or so. All the gold ornaments, right, they are cast. So you can imagine what is the length scales in casting, and casting any size you can imagine can be cast. In fact, most of the big products, if you see them, the huge machines, right, the structures of the huge machines, they are all cast. The tolerances can be from 0.005 inches to 0.1 inches. And the surface finish is in die casting. I will tell you what die casting is in a little bit, and what is sand casting. So die casting is if you have a permanent mold. So you can take a steel mold and inject aluminum or brass in it. That will be die cast. So most of your, if you see all the products in plumbing, you have seen plumbing products, right? Your faucet, your taps, these are all die cast, especially if it's brass and aluminum. Steel die casting, you'd need something of very high melting temperature. So steel, still a bit difficult, but aluminum, brass, you can do very good quality die cast. So these are some of the processes which are there. You have sand casting, shell casting, plaster casting. What I will do is let me just show you some of the videos of these processes. So sand casting, you all know, right?
Yes, sir. So one guy told that he doesn't understand the sand casting.
So can you unmute yourself and tell me what exactly you don't understand in sand casting, and then I can tell you what is it that you don't understand.
Sir, I don't know the whole terms. What is the sand casting? I know
I showed you a video, right? In the beginning, that there are two boxes. Let me just go ahead and first explain what sand casting is. If you have not understood, maybe a lot of other people also would not have understood. Let me just explain step by step what is sand casting. Just give me a minute, and then we'll go back. So sand casting is if you want to create a product, right? So first what you do is you need a pattern. How many people don't know what a pattern means? Whatever shape you want to create, right? You need to cut it into half. Imagine I have to make a ball, right? I have to cast a ball. So I will take two hemispheres. Get me? Take two hemispheres because I have to take this ball out. If I have to make a ball, right? If I have to make a solid ball, what kind of cavity do I need? Tell me. What kind of cavity do I need?
Hemispherical.
Yeah.
A hemispherical cavity, right? Full hemispherical cavity, right? Yes or no?
Yes, sir.
Yes, sir.
So now I will take two hemispheres. Imagine this is a hemisphere, and then I will take a box, and I'll basically put sand on this box. Then I'll ram the sand with the ball. So imagine this is not a this thing, but a half ball. Then I will make this. Then I will flip it, right? And then I'll put the other half of the ball on the other side. And then what I will do is I will take so this one is very simple geometry, right? This geometry is only, I'm making a, what is it called? Just a rectangular kind of a thing. So I can just take the mold out like this and then put more sand into it and cast this kind of a part. But and then out comes this kind of a part. But if you imagine, I have a more complex part, say I have a ball. So what I will do is I will put in this box, in this, let me just show you something like this with the pointer option. I'll use half ball here, half ball here, and extract it. Let me go back to that video again. So sand casting is only sand because you're using sand there. Let me just go back and then show you this thing, how to extract the, if you don't remember that. Sorry.
To make a hollow metal casting, we require a pattern supported by a core and a core print. This demonstration provides useful way of understanding the following steps. Take a hollow boxes, rectangular in shape.
So one is called cope, one is called drag. The two boxes.
As shown
so this is the half pattern. So you'll put a ball there, half the ball there, and pack the sand.
And compactness.
And this sand will not be natural sand. This will be with the binder, so that when you pack it, this sand will become almost like a solid, right? And then you take, then you basically put the other one. Put the other box on top of it. The bottom one is drag, the top one is cope. And then you put the other half pattern on top of it. And then put the sand, ram it. So now you have the pattern inside these copes and drags totally rammed. The sand is packed. You ram it with the with some sort of a ramming device, like a muscle.
And remove the pattern.
And then you flip it open and then take both these out. So now you have a cavity. And this cavity is surrounded by sand. Okay. That's what sand casting is, because you are creating this cavity in two boxes full of sand. And those boxes are termed cope and drag. Okay. I'll stop this here now and then go back to this. So now you get what sand casting is, right? Anybody who has not gotten sand casting? Okay, good. Very good question. How is the pattern made? So pattern can be made by machining, by somebody who is very skilled can carve it out of wood. Right now it is done by 3D printing. You can take a solid model, do a rapid prototyping, 3D printing of it. You can do a machining of it. Or if somebody is very creative, because back in the day, somebody had to make the pattern, right? So somebody would make the pattern in wood. That's what they would do. You get me?
Yes, sir.
Yeah. So there are multiple ways to make the pattern. A, you can do 3D printing. B, you can do machining. C, you can do woodworking. D, somebody can give the shape by shaping the wood, right? Like if he is very talented and because back in the day, the entire shape pattern was created by hand. People, the shilpis had the skill to do it. Today, probably not, right? So that is what sand casting is. So sand casting requires, let me just go ahead to sand casting. I've shown you, right? Now you know, everybody knows what sand casting is. So there are multiple ways to do casting. Sand is just one of them. You can do shell casting. So let me just wait and show you some videos of shell casting. Shell casting is also a very interesting process. I'll do shell molding process. So they take a metallic pattern. Okay. So shell. So can somebody tell me what is the difference between sand and shell casting? You saw the video, right? Can somebody tell me what is the difference between sand and shell? Anybody?
So we have to create the half part separately, not at the same time.
No, but then you do that the same thing in sand casting also. You have two half patterns.
Sir, no need of core for any hollow.
Core is there. Core is there. Everything is there. You make a shell out of that. So you mix the sand with the resin, and the resin cures. So instead of having the copes and drags, you get a shell, complete shell of the sand with the resin mix. You get me?
Yes.
So you get a shell, like there is a solid sand and resin. Resin, you know what resin is? Some people don't know what resin is. Yes, final product is hollow in shell casting. No, the shell casting is just a shell. Instead of having two boxes and a cavity, the cavity is in a shell. That's the basic difference. So the shell, what they do is they will have sand, and sand is mixed with some resin. Resin cures at higher temperature. So resin basically is something like araldite. How many people have seen araldite or MC? Everybody knows about araldite and MC? Yes or no? Who doesn't know what araldite or MC is?
No, sir, I don't know, sir.
Have you used Fevikwik?
Yes, sir, yes, sir.
No, if you leave Fevikwik, it hardens.
Yes, sir, yes, sir.
So in epoxy, basically in resin, what happens is if you heat the resin will solidify. Either you leave it for some time or you heat it at a temperature. So that's what resin means. So if you have sand mixed with something like Fevikwik and you heat it, it will become a solid piece. So if you let me just go ahead and show you the shell again. So basically all it does is see, it takes a metal shape, whatever you want to create, metallic pattern. You heat the metallic pattern and you have a sand and resin mix. So it will go ahead and it will stick to it. And it will stick to it. And then you get a second half of it. Because second half you are doing it if you need a core. Right? The second half came. Now you can, so you have two pieces of shell. You combine the two pieces, tighten the two pieces together, and pour the metal there. Exactly same. And you can put the core if required. And then pour the metal. You get me? It's exactly the same process as sand. The only difference is that what they do is they will instead of having two boxes, you have a hardened shell around it. And you need two pieces again because you have to take the pattern out and you have to put in a core if required. So it always needs to be in two like cope and drag, right? It needs two sections so that you can withdraw the pattern out. Okay. Any questions about the shell one? It can be hollow in shell casting if you have what? If you have a core there. So you have to leave the core there to create the hollow pattern. Otherwise, you will get a solid thing. The product is not shell. The casting mold is a shell. It's not a solid box, but just a shell of whatever you have, or whatever shape you want. So that's why it is called shell. Similar process, just you use a resin to create a stiff shell, a thin thing which will create a cavity of whatever part you want. Does it make sense? You got shell, right? Then there is plaster casting. This plaster casting is also what you do is you use this for low melting temperatures, for creating brass statues or aluminum things. If you, I don't know if you have noticed those people who sell small statues, metal statues, the Banjaras, they actually do this plaster casting. I'll just show you the process. Yes. So plaster casting actually takes, see, if you want your hand casting, you can do your hand casting also. A lot of artists do it. You'll put a plaster around your hand and then take the, at least you have to do two pieces to basically take it out actually. So instead of having a sandbox, your mold is made of plaster. That is the basic difference. But then the flip side is you cannot use very high temperature material to mold here. You will use only lower temperature, some like bronze, very low melting temperature material you can use. So it's just exactly the same kind of a thing. They will show you how what kind of feature they want to cast. They will open the box right now, and then you'll be able to see it.
So there is a question, is this plaster of Paris?
Yes, this is plaster of Paris. Yes. Just solidifies. The only flip side is you cannot use it for high temperature material. You cannot use it for steels or iron. See, they will show you. They'll open it and then they'll show you what kind of feature they want to do. So this is the shape they want to create. They will get another half of it and then they pour the material. So this is the shape they want to create. So this is the cavity which will fill with metals. Okay.
The cold.
So this is the plaster of this is plaster molding. So instead of creating the mold out of sand, you create the mold out of plaster. And then let me just show you this. The quality will not be very good, but you have to bear with me.
Chamber machine is used primarily to die cast the aluminum, magnesium, and copper alloys. In the cold chamber machine, the charge is supplied by ladle or feed system from an external furnace source to a holding pot at the shot end of the machine. The feed system components are not submerged in the molten metal. The charge is poured ahead of the plunger tip through a pore hole in the shot sleeve. As the plunger advances, it closes the pore hole and drives the molten metal into the die. After the metal in the die solidifies and the die halves are separating, the plunger thrusts forward, extending the plunger tip past the cover die. This pushes the biscuit that solidifies at the end of the shot sleeve, assisting casting release.
So die casting is, the difference between die casting would be that you will have a solid mold, maybe a steel mold, and you can do aluminum casting. So there is a permanent mold, and the material will be pushed through a plunger to fill the cavity, and then you need to take the material out. It will split open once it solidifies, and then you can take the part out. So a lot of these faucets, all these plumbing equipment, a lot of these taps, faucets, they're all made using this technology, right? Any questions? Is it clear what die casting is? And then I'll talk about semi-solid casting is nothing but you basically make the material in while it is flowing and then form it. So it's a basically combination of forming. Forming basically means deformation. I'll talk more about it when we go to forming. You will get to know more, but it's a combination of a deformation process and casting process. And then
Sir,
let me show you another video here.
Again, the die casting.
What is?
Re-explain the die casting.
Okay. So what did you get? What did you get in die cast? What did you get in die cast? What did you get? Like, what did you understand in die cast, and what was it that was not very clear in the die cast? In die cast, what happens is you have a permanent mold. You have a permanent mold, right? And then that permanent mold, what you do is you have to fill the permanent mold cavity. Yes or no? How do you fill the permanent mold cavity? What are the ways of filling it, in your opinion? I can pour it. So the gravity head will let the mold be full, right? There's one way to do it. But if I'm making very thin materials, right? Very thin shapes. So if I'm making a faucet or a tap, right? You know, the wall is very thin for the faucet. Will the material go there in the cavity very easily? Yes or no?
No, sir.
So what will I do to make sure that in a very thin cavity the material flows? What will be a way to do it?
Sir, either by making it pure fluid or something, applying pressure.
So you have to apply pressure so that pressure driven flow goes into so it's like a flow through a annular pipe, right? But you have to give a pressure gradient because pressure is what drives the fluid, right? So I'll have to give a plunger. So I give a plunger. This plunger, what it does, it pushes the fluid into the cavity. When I'm doing sand casting, the gravity head alone, right? I have the velocity due to the gravity head. Whatever I'll pour from a height, and that height would give me a gravity head, which will give some velocity, right? Root 2g st. I'll analyze that. I'll show you some analysis. How do you get the velocities in sand molding? But in thin castings, right? Like die casting is very thin. Thin shapes are made. There you need a physical pressure to get the material into the mold. Let me run the video again. I think it will be a bit clearer to you.
The cold chamber machine is used primarily to die cast the aluminum, magnesium, and copper alloys. In the cold chamber machine, the charge is supplied by ladle or feed system from an external furnace source to a holding pot at the shot end of the machine.
Okay, and there is a plunger.
The feed system components are not submerged in the molten metal. The charge is poured ahead of the plunger tip through a pore hole in the shot sleeve.
So you have,
as the plunger advances,
now
it
material is
closes
being
the pore hole
pushed by the plunger
and drives the molten
to
metal
give pressure
into the die.
so that it fills
After
the cavity.
the metal in
So
the die
this is the shape you have to create,
and
right?
the die halves are separating,
So you have to fill the material
thrusts
there.
forward, extending the plunger tip past the cover die.
Okay,
This pushes the
is your
biscuit
part.
that solidifies at the end of the shot
This
sleeve,
is your part.
assisting casting release.
So now you understand what this die. How was it pushed away to the metal separated? What do you mean?
So just now the plunger tip goes ahead and pushes it and it just what is
So
that?
once it solidifies, right? So the plunger pushes it initially to get the liquid inside it. Once it solidifies, it pushes further so that the material gets out of the mold, because material has to get out of the mold, right? So one mold it will push further so that it gets out from one mold, and other mold we can pull it, or there will be a push pins from the other side. It will push the mold out. because it has to be taken out, right? So this plunger does two things. Once it pushes the material to fill the mold. Number two, when it solidifies, it just pushes it out of the mold, because mold is a two-piece thing. Can you visualize that or no?
Okay. So it just gets out of the mold when it's pushed out.
Yes. So after solid, so this will initially push it to make sure that the mold is full, right? And once it solidifies, it will push it further, so that it comes out from the one half of the mold. The other half, there can be push pins which will push the product out, and the product will come out of the mold. Because you have to open the mold, right? So this opening method is that this plunger pushes the material out. So the second mold will go back, the plunger will push it further, and then from the other side there will be two pins which will come and push the product, and the product will fall below on the product line. So that's how you will keep on casting it and moving it out. So there will be a conveyor to carry the finished product. Can you visualize it now?
Yes, sir. Thank you.
Okay. Let me now go to this. Then there is investment casting. All the jewelry. How many people know how the gold jewelry is made? Anybody knows how gold jewelry is made? All of us gift gold jewelries on occasions, on weddings and whatnot. Anybody knows how is gold jewelry made? How do you make this gold jewelry? Anybody? Can you tell me how a gold jewelry is made? Somebody should know, right? Nobody knows? So if you don't, it's made by something called investment casting. So I'll actually show you how investment casting actually works, so that next time somebody asks you how gold jewelry is made, you can talk about it. Did you guys notice how investment casting works? How many people understood how investment casting works? Anybody?
Sir, can you please rerun the video? Like I get a little bit.
Let me rerun it. Okay. Watch it carefully.
Sir, the video is the different one.
Okay.
Plaster.
Okay. Did you get what it does?
Yes, yes, now it's clear, sir.
What is it? Can you explain it to the other people?
So like first a pattern was made with the help of the wax, and then we
Why
want to
wax?
create a
Why wax?
hollow thing.
Why did they use wax?
Sir, the wax is simply used for the creating a pattern so that we can get the hollow substance after
Why
making
not
the
wood?
wax.
Why not wood? Why wax?
Sir, while heating it melts down and goes.
Yes, sir.
So you want a low temperature thing. You need a wax just to coat what is it called? Ceramic
Yes, yes,
slurry
yes.
around it, right? As you did it in the plaster. It's very similar to the plaster one. No, sorry, shell one. I'm sorry, shell one. So you take wax mold, put it into a slurry. This slurry wraps around the wax mold, and then what you do is you bake it. When you bake it, it will evaporate the wax and solidify the sinter the ceramic mold. Then you can pour your material on top of it. Okay. So that's what this thing is. Let me just quickly. Okay. I am sorry.
Sir, your voice was not coming.
Sir, you are on mute.
Hello.
Sorry, I think I lost you there for a minute, right?
Yeah.
Yeah. So there is sand mold. You understand now, right? Shell mold. Do you understand? You understand the shell mold where we are using resin plus sand. Resin plus sand. Plaster. You know we are using POP here. Ceramic is similar to that. Investment. Ceramic, well, there will be a ceramic mold. That's it. Investment actually uses some sort of a ceramic mold in the same fashion. In the same fashion as you do it here in the shell. All you do is you do this. This is you here you use a metal. Here you use a metal pattern, heated metal pattern. Here you use a wax. It's also called lost wax. Lost foam is also very similar, like lost wax only. Pressure and vacuum are die casting processes. In die casting, you have a permanent mold. You have a permanent mold. And since there are thin pieces, you need pressure there. You need pressure to push the fluid. Push the fluid here. Right? Squeeze again is where you squeeze the material in. Semi-solid is a combination of casting plus forming. Then there is something called single crystal, which is used for turbine blades. Turbine blades. There what you do is you allow, while casting, you allow only, you constrict it, you allow only one grain to pass, and you put a chiller plate here, you cool it here. You cool it here and only one grain comes out. So the entire material is just one single crystal. This is a technology which is very critical. Can anyone tell me, if I have a single crystal and if I have multiple crystals, what will be the difference in the properties?
The creep property will be better than single crystal.
Huh?
So, creeping, difference in the creep.
Difference
properties will be better.
Properties will be better. Let me bust you the bubble. The property is actually inferior to a multi-crystalline. At least
No, sir,
the yielding property.
I'm talking about I'm talking about the creep properties.
Yeah, so only
Properties to
thermal
creep.
creep is better. Only thermal creep is better. So this can be used in turbine. So single crystal like typically is in turbine blade. So you need to, and directional solidification is just inferior to single crystal. So first people used normal multicrystalline. They went to directional solidification where there was crystals in one direction. And then they cast something called single crystal, where single crystal has very good thermal creep properties. So at high temperature, the material doesn't deform automatically, which happens in multicrystalline. So if you have multiple crystals in a material, these crystals will glide under high temperature, which doesn't happen in single crystal. So single crystal is something, and then there is something called continuous casting, wherein I'll just show you, you can create casting, and all the steel plants have this continuous casting where you can create features right away. Let me just go ahead and do this, share this again, so that you can see the casting video. Continuous casting. Can you see my screen?
Yes, sir.
Which one? The process one, or processes one, or the video?
The VLC one.
The VLC one. Good. That's what I wanted to show you. Videos.
Steelmaking primarily involves the removal of impurities from iron and scrap metal and the addition of desired materials. This process occurs in a furnace at extremely high temperatures. Steel leaves the furnace in liquid form and is then shaped into flat slabs and other useful shapes. Steelmakers may form slabs into long sheets by passing them between heavy rollers. The sheets are then rolled into coils for shipment to the customer.
So continuous casting basically means is that there would be, when they pour the material, it freezes and then it is rolled. So you pour the material, it freezes, and you can roll it right away. So you don't have to cast billets out of it. You don't make billets, right? So then you can do it continuous, keep on casting. As you pour it, it solidifies, and then you roll it in the hot condition, and then keep on. So that's called continuous casting. You don't have to create discrete billets out of it. Get me? So that's what continuous casting is. And let me go ahead and then unshare this and share this again. Okay. Okay. So now you're clear with the processes, right? All the processes. How many minutes do I have? Do I have some time? Or no?
So 4 minutes.
Okay. So let me just do a couple of slides. So sand casting is 60% of the processes. Investment is 7%, primarily for critically the tolerance and the surface finish is very good here in investment casting. Die casting is another 9%, which is for mainly faucet, taps, and plumbing supplies. Permanent mold casting is similar to die casting is also a permanent mold casting, but here what you can do is you can have reusable molds, unlike sand. Reusable molds, but you don't use die casting. Typically, you would have pressurized flow here. Then instead is centrifugal casting, wherein if you have a symmetric thing, radially symmetric thing, you rotate the material, so the material can. So here you can make cylinders out of this centrifugal casting, cylindrical shapes, so that you rotate and the fluid will flow radially outward. That's centrifugal casting. And then there is shell mold casting. Shell mold, I've explained to 6%. So still, major chunk is still sand casting. So the basic steps in casting are, first thing is you need a pattern, you need a core if it is hollow, only if it is hollow. And then you need molds. You need to melt and pour of the liquefied metal. Then it solidifies and cools at room temperature. Then you remove the casting, you shake out. And then you inspect for possible defects. Pattern is exact replica of whatever you want. You can create, you can either use metals or you can also use wood for that. But if you want to cast, you need to create the cavity, right? Same cavity. And the cavity is done by pattern making. This is the last slide where I will stop, and then we'll take it in the next class. One of the key things is, what is the size of pattern I need? Let me just give you a thought question and we'll quit here. What is the size of the pattern? Do I need the pattern exactly the same size as my object which I need, or it will be different? Just thought question, and then we will quit here. This is the last question. Can somebody tell me, and then we'll take this. Should the sizes be same? Pattern should be made exactly the same size as the object which we want, or no?
A little bigger, maybe.
Why little bigger? It's a very good answer. You've answered it correctly. But why do you want to make the pattern a bit bigger?
Molten metal is poured, right?
Huh?
Molten metal is poured, right? After cooling, it may shrink.
So there will be shrinkage. So you have to account for shrinkage. What else? You also have to machine it, right? As cast, the shape doesn't really is that great, right? You have to machine it. And the second thing is, we also want some allowances to take it out, right? Because I want it to take the pattern out, so I will have some sort of a draft allowance to just take it out easily. I can't make it even if my product is straight, right? I cannot make my pattern straight. If I make my pattern straight, if I wiggle, I'll damage the mold. I want the pattern to get out very easily, so I'll give a draft tolerance there, additional. So these three things would require on pattern. We'll stop here, and next class we'll do some analysis. Okay, let me stop here. Thank you very much, and we'll meet tomorrow at 11:30. Bye-bye. I think